Right.
All right. All right. Good morning, good afternoon, good evening, everyone. My name is Boyang, and this is our show and tell news session, hosted by Pages ECN North America Early Career Representatives. So it is our honor today to have Natasha and Riley here to introduce their fascinating stories. Um, Natasha is a low temperature geochemist and paleoclimatologist. She's a postdoc fellow at Brown University working with Dr. Dan Ibarra. Um, she's in general interested in the karst and spelothem sciences and investigate the terrestrial hydroclimate on seasonal to millennial timescales. For her postdoc project, she's focusing on the history of droughts and floods in the Philippines. Um, I bet we're gonna hear some story about that today. Before she joined Stan's group at Brown, Natasha received her bachelor's degree at the University of California, Irvine. Later, she earned her master and PhD degree from University of Texas, Austin. Her PhD work explored stalagmites from the near entrance cave setting in New Mexico, USA. And also, she's gonna join the geology department at Occidental College in the coming spring semester, which is great. Um, so Riley Havel is a first-year PhD student at Brown University, working with Drs. Gary Boudet and Dan Ibarra. Her current research focuses on mass-independent triple oxygen isotope fractionations in meteorites. Before joining Brown, she received her bachelor's degree in physics from the University of Central Florida. She will give us a lab tour of their triple oxygen isotope lab right after Natasha's presentation. So with that, I'll let Natasha start with her journey in Philippines. Thank you.
Great. Thanks, Boyang. And thank you, everybody, for joining. I apologize. I have a bit of a cough, so I might mute myself to cough in between. But very excited to present to the community on the research that we are doing in Dan Ibarra's group. And Riley will be later on talking about giving a first-hand experience on running a triple oxygen line to get data. So today I'm mainly going to be focusing on this project that we started about a year ago now, and just a little bit about the logistics of what it means to get data out of caves and setting up monitoring stations and the kind of local support it involves. And we are just getting data now for this project. So I won't have too much slides or too much details on the results, but stay tuned as we will be presenting the results in upcoming conferences at Goldschmidt and then also at GSA and AGU. To get things started, I've spent, as Boyang was saying, a good part of the last decade looking at this cross-section. So I've spent a lot of time thinking about the processes that are driving the formation of karst landscapes and also how climate is being recorded within the karst landscape. To give a quick overview on what we mean when we talk about karst landscapes, it's a type of landscape that is formed by the dissolution of soluble rocks, including limestone and dolomite. More than 25% of the world's population rely on water that is acquired from these karst aquifers. And I really believe a source to sink investigation allows a unique perspective into processes driving climate variability. So really understanding this link between the rainfall above the cave, how it permeates through the rock above the cave, and then finally gets deposited as calcite precipitated into speleothems. In our case, we are interested in stalagmites, which grow from the ground up. So understanding this process as a holistic, I think, gives us a really good understanding on terrestrial paleoclimatology. So as a researcher, I am interested in three aspects. So understanding the modern climatology, understanding the carbonate critical zone, and as well as understanding the paleoclimatology and really thinking about the questions that we can ask in this dynamic landscape. This is a really neat paper that came out recently that talks about global karst distribution with published speleothem records. So what you see over here in the darker gray shading is a global distribution of wherever you have karst landscape. The purple hexagons, I should say the purple pentagons, are published speleothem records that are available to anybody. And the turquoise kind of circles show active monitoring sites. So where studies are monitoring the modern systematics of caves to tell us something about the climate in modern times above the cave. And the pink squares are published identified records, but they are not publicly available. So if we really zoom in to the Philippines, which is where I'm doing a lot of my postdoc research, you'll see that there is a lot of karst in that country, but there's only one published record that came out in 2015. And since then, there's nothing that's been published, and there is currently no active monitoring that's happening in that region. Which is interesting because around 9% of the total world population lives in Southeast Asia. Manila, which is the capital of the Philippines, ranks number 5 as the largest population areas, which falls right over here. And in addition to that, there are a lot of recent research that show that these tropical island nations in Southeast Asia are highly vulnerable to the impacts of climate change. So the darker the red colors indicate higher climate change vulnerability. This was a paper that was published by the World Bank. So you can see the Philippines, the entire country is red. So what that essentially suggests is things like damaging cyclones, droughts, extreme precipitations related to monsoon events, and also ocean acidification are all expected to increase and are expected to exacerbate because of global anthropogenic climate change. But there is minimal research being done on what the past terrestrial climate or past terrestrial paleoclimate tells us about these periods of change. And that's why we were interested in going into the Philippines and setting up monitorings at different cave sites and also collecting stalagmites to piece together a history and try and understand how these trends have changed through time. So essentially what we do, going back to sort of the 3 forks of the research that I do, I'm interested in discerning modern climate drivers, which are driving hydroclimate variability. I'm interested in building empirical relationships between the proxy, stable isotopes or trace elements, and the climate. And we do that by actively monitoring the cave, and I have a few pictures for that. And that ultimately leads us to be able to answer questions on how ENSO variability, how monsoon variability, and also how fire dynamics have changed through time in order to constrain future projections. So jumping into the Philippines and trying to understand its modern climatology, it is a country that has over 7,000 islands. It is not a climate monolith. There are 4 major climate types. You have climate type 1 and climate type 2 that hug the eastern and western shorelines. These 2 climate types have unimodal rainfall seasonality. So you have the southwestern monsoons, which peak in the summer, and then you have the northeastern monsoons, which peak in the winter. And these are the ones that characterize this unimodal rainfall variability. Climate type 3 and 4, which are this darker green and the blackers, they don't really have a strong rainfall seasonal signal. So what we are doing right now is we set up monitoring stations in almost like a 10-degree longitudinal spread, latitudinal spread, and we are going from 1 to 2 and to 3. Those are the 3 main caves we are monitoring, as well as we have collected stalagmites to understand this difference between the northeast monsoon as well as the southwest monsoon. I'm going to talk a little bit about the third site, which was we went there in December and did an overnight trip in the cave to collect these stalagmites, and why we had to do that I'll talk about really briefly. But this is a UNESCO World Heritage Site, and we have to take a speedboat from this wharf, Sabang Boat Terminal, and make our way across the island to land on this beach, from which when we have to take kayak style boats and go further inside. So talking a little bit about Puerto Princesa, it is the second longest underground river system in the world. It's around 12 kilometers in length. That first orange dot that you see, that is the entrance, which is where we entered the cave from. We have two monitoring stations. One is gypsum galleries. It's about 4 kilometers from the entrance. And then we have the Gaia Passage, which is about 2 kilometers from the entrance. So given the length and the difficulty of getting to the cave is the reason why we ended up spending a night inside the cave to make sure we have achieved all of our scientific objectives in terms of making sure our instruments are monitoring the way they are. And we were also taking out huge and heavy amounts of stalagmites. So just to make sure everybody was comfortable and well rested, we ended up spending a night in the cave. So this is entering the cave. It is open to the public, but only on guided boat tours. And we were working very closely with the National Park Rangers to be able to go to spaces and to go to chambers where tourists are not allowed. After the section, so the cathedral is where the tourist boats essentially turn around and they make their way back to the entrance, and we go further in. And there is this stark contrast between headlights from the tourist boats to complete darkness, and all we have guiding us then are our own personal headlamps. So this is right over here, about 1 kilometer from the entrance. So gypsum galleries, which is about 4 kilometers from the entrance, is indicated in this orange circle over here. And this is a video, again, just showing we station our boats on a beach, and pitch darkness, that's another group making their way into the chamber itself. And inside the chamber, we currently have permits to collect broken stalagmites. So this is Jones, who's in charge or the head of the Cave National Park Ranger team. And we worked with him to sort of isolate and see wherever there were broken stalagmites. And they're absolutely amazing. They're really, really tall. So the idea of getting a continuous paleoclimate record is super exciting. So we collected 3 broken stalagmites from this chamber. And that's me kind of investigating the validity or the fidelity of this stalagmite. How good or bad does it look in terms of getting a clean geochemical signal? Following that, we went back towards the entrance, but we didn't actually go to the entrance. We took another sort of parallel river path and went up to the Gaia Passage. And that is where we set up camp. So we had to swim 150 meters in this muddy water to get to a landing where we could then walk towards our area. That's me. We set up sort of sleeping stations. And then that's Bryce. He is a graduate student at Vanderbilt University and has extensive caving experience working in different caves from in Tennessee, as well as Mammoth Cave National Park. And then we also had a team of 7 local cave rangers who took all the sort of sustenance. They took care of all the sustenance requirements. So in terms of making sure we had enough food, enough water. And then these were also the people who were guiding us through the different chambers to take us to this broken stalagmites, because we are scientists and we don't really know where we will find these broken stalagmites. So it was very important to build trust and relationships with the local cave rangers. So we have multiple ongoing projects. We collected 13 speleothem samples. This is a picture of all of them that we got back through customs, and we have all the paperwork for that. In addition to that, the team is also monitoring and collecting water for us. This image over here shows Gerald, who is collecting drip water for us every month. In addition to that, we are also collecting plates. So these are plates that we leave under actively dripping sites, and we leave them and then collect them every 2 months. And what we are interested in is the calcite that is precipitated over those 2 months. We scrap that out and analyze that for stable isotopes as well as trace elements. So this is from where we build this empirical information or get this empirical knowledge on the climate above the cave and the geochemistry of this pseudo stalagmite. So this is a really cool video. So you have active drip, and that drip leads to active modern cave precipitation, which allows us to backtrack and see if there are any seasonality differences in what the stable isotopes is saying versus what's happening in the climate above the cave. And this is we just finished sawing some of these speleothems that we brought back with us. And this is a cross-section image of a thick section. It's about 1.5 centimeters in thickness. And you can see really beautiful laminations, really clean calcite. And we are very excited to now age these stalagmites and actually see how old they are. But given that these are continuous and relatively big candlestick stalagmites, we are hoping to get really long-term growth in both of them. So essentially, we will be doing traditional stable isotopes, looking at oxygen-18 and carbon-13 to better understand hydroclimate variability for oxygen, and then also vegetation changes via carbon, and then also looking at trace element concentrations via laser ablation, ICP-MS, and specifically interested in alkaline earth metals like magnesium, barium, and strontium, and also transition metals such as iron, copper, and zinc to tell us something about more local effects that have impacted the epikarst. Something that's really exciting that Dan has been working on, I haven't worked on with him on this yet, but I hope to within the next month or so, is the non-traditional stable isotopes, looking at triple oxygen, which is another proxy that can be used to discern the different parameters that affect oxygen. So when you're looking at the delta O18 of oxygen in stalagmites, it can be impacted by the amount of rainfall, the moisture source, the relative humidity, the temperature of calcite precipitation, and it just using oxygen O18, traditional oxygen, it's hard to back calculate which of these parameters is actually driving this variability. Triple oxygen comes in, and what that allows us to do is really backtrack and see whether it is really fractionation, whether it's cave kinetics, or whether it is this moisture source change, evaporation, or seasonality difference that is driving the variability in the delta O18 of the speleothem. These are some really new papers that have come out by researchers across the world that are trying to really bring down this framework on how to use triple oxygen to interpret the delta O18 of speleothems. So I think this is, Riley, if you want to take over and walk through how we actually get triple oxygen data, I will let you do that.
Yeah, Natasha, do you mind coming into the lab to hold the camera, or do you want me to? Okay, great. So Natasha's just down the hall. It might take her a minute to get here. But while she's walking over, thank you for the introductions and for letting me participate today. As Boyoung mentioned, I'm a first-year PhD student here in the Department of Earth, Environmental, and Planetary Sciences. And my primary research is focused on isotopes and meteorites. I've only been in this field for a few months, so this has been my primary experimental work. I've been working on the laser fluorination line in Dan's triple oxygen isotope lab. So Natasha has made it. Let's make sure I can switch around. Great. Perfect. Awesome. Okay, so I figured the best way for me to show you all the work that I do in the lab is to take you step by step through what I do to prepare a sample, to weigh out the sample, and then to analyze it, and give you a thorough description of how the setup works and what I know about the line so far. Great. So the first thing that I need to do when working on a sample is prepare it. So I know every sample needs to be prepared a little bit differently. For my case scenario, looking at meteorites, we typically leach them to remove terrestrial contamination. Now, when you're working on terrestrial samples, I'm under the impression that that is a very different process. But regardless, it'll start somewhere in a hood with whatever preparation methods you need to do. And in addition to preparing the samples in the hood, we clean different aspects of the experimental setup that I'll show you later, so you'll get a better visual idea. So then we go over to the weigh table, and normally for my samples, I'll weigh out 2 to 3 milligrams of sample per analysis. I know for terrestrial work, it can range from 6 milligrams-ish up, plus or minus. And so that's one key difference to note, is that the method that you choose to use, whether it be using the bombs on the line, which is right over here behind us, whether you're using the bombs or you're using the laser to react your sample, it'll change how much sample you need to be using. So in general, the fluorination line has 2 options for where you place your sample and how you start. So you can either use the bombs, which require a little bit more mass, or you can use the what we call a laser chamber down here. And so this only requires 2 to 3 milligrams. And the key difference between these two is the amount of time that you're reacting your samples for and the temperatures that you're reacting your samples at. So in the bombs, you place your samples in here and you heat them up for around a day, a little less than a day. And you react them with bromine pentafluoride. And in the laser chamber, you only react your sample for less than 5 minutes, but at much higher temperatures because you're using the focus beam of the laser, but you're also reacting your samples with bromine pentafluoride. So I'll start at this end of the line back here. So in these 2 Teflon containers, we have the reactant bromine pentafluoride. You can maybe see this slight yellow coloring. It's really difficult to get like a visual on, but I promise you it's in there. And so bromine pentafluoride has been used for laser fluorination and triple oxygen isotope analyses since the 60s, so going on 60 years. There are other reactants that you can use, other fluorides or just fluorine, but bromine pentafluoride is really great because it's liquid at room temperature, it's highly reactive, and it has a really high vapor pressure. So it makes it a great option for us when we're finding something to help us dissolve our samples. So how it would work is I would isolate either the chamber or the bombs. So to isolate it, you normally just have to turn the knobs somewhere along the fluorination line. So when I say fluorination line, I mean anything that is connected by this metal piping that you see here. So I would isolate my samples in the fluorination line just by opening or closing different valves. And then I would open the valve to the bromine pentafluoride, so here, and because
Sorry, Riley, you are muted.
Yeah. You guys are muted.
the
Oh, here we're
to the
back. Okay.
computer, I'll show you all what it looks like. So here is a visual of just one corner of our sample holder. To give you an idea, there's 6 or close to 10 holes within a sample holder. So you can analyze like 10 samples in a day for the analysis that I've been doing lately. And you can use the software to move around within the sample holder and direct the laser where you want it to go. So after I've got my reactant in the chamber with my samples, I'm ready to lase. And so I will turn on the laser, ramp it up to a certain power, and then I'll use just this set of crosshairs to point and fire. And the lasing takes less than 5 minutes, and you'll be able to see your sample dissolve as you go. It's super exciting, and sometimes with different kinds of samples, depending on the mineralogy, you'll get leftover fluorides, or you'll get leftover materials. So for example, quartz tends to lase really, really nicely, and you're left with nothing. But this sample was probably a meteorite, and you can see some black specks, maybe some silica gel beads, then a white kind of like covering of these fluorides. And so this is what happens after you lase every sample. So I'll go back over to the line. So once the sample has been lased, this will have been isolated, and within this section of the chamber, we'll have the remaining bromine pentafluoride, so whatever wasn't used in the reaction. We'll have some of the leftover reactants or products, like whatever else is in there, and then we'll have molecular oxygen. So the part that we're really interested in isolating is the molecular oxygen, and luckily, some chemical properties of everything else that's in the line with it makes it easy for us to separate that. So what I would do is I would fill up one of my dewars with liquid nitrogen, stick it on this track, and I would wait for it to stop bubbling, indicating to me that the reaction has been completed and everything that is going to freeze will have frozen. And in theory, all that will be left as a gas in the line is my molecular oxygen. So I would open these one by one until I get over to this trap, which is a little bit thinner than the traps that we have throughout the rest of the line. These two are just backup liquid nitrogens to collect any remaining waste that didn't react. This is the salt trap that we have heated. So this reacts with some of the other waste in case it wasn't taken care of initially. So by the time our sample gets pulled all the way across the line into this trap, it's relatively pure. So within this trap here, we have these little minerals called zeolites, and they have a pore space within their mineral structure that readily accepts molecular oxygen. Very convenient for us. So glad that this is something we can use. And so what I'll do is I'll freeze this trap as well, and all of the molecular oxygen will get collected into the pore spaces of the zeolite. So as a scientist, you might be thinking, how do I know for sure that this reaction is happening? And as a user, you want to be able to maintain like a really great understanding of what's happening at all times. So for me, I'm so grateful that we have these handy dandy pressure gauges. So normally after the reaction, this gauge will be at about 80. And once I freeze down my waste, it'll be at about 40. Once I expand the whole volume, it gets down to 6 or 7. And I can watch it drop down to 0 as my molecular oxygen is collected into the zeolite. And so I know that all of my oxygen is safe and ready to transfer once I see no pressure left on the pressure gauge. So then I will go ahead and isolate my oxygen. You always want to protect your sample. So I'll isolate it, and my next step will be to run it through a gas chromatography column. So that's contained within this mystery box. Currently it's being heated, so you heat it up after every run to get rid of any contaminants. But what this does is this allows me to remove any interferences that might be on oxygen 17 as a primary interference that we're concerned about. So this cleans up our sample in case anything didn't freeze down or in case the zeolite has something in it. So this allows me to purify my sample even further. And I use a helium gas to pass my sample through the gas chromatography column and then to pick it up from this zeolite and move it over to another zeolite. So in order to get the oxygen so it's ready to transfer, I would thaw this zeolite and freeze this zeolite. And this will help the zeolite or the oxygen be pulled into our second zeolite right next to our mass spec. So once that's done, I'll isolate my sample here and get it ready for analysis in our mass spec. So the mass spec, we have this chunk of metal here contains our source. And so this has a filament which will ionize the molecular oxygen so that we can pass it through the mass spectrometer based on its mass to charge ratio. So I will turn the source on, it's ready to go. It ionizes my oxygen for me, sends it through the magnet and then into each of the cups, which are designed for the triple oxygen setup. And meanwhile, I will thaw my liquid nitrogen. And yeah, sorry, Natasha, we'll focus in on this screen. So this is what it looks like inside of the mass spec. My sample will come in through this valve here, and then I will thaw it into this bellow. So we've got two bellows. On the right-hand side, we have our reference gas, which is constant. We measure it against itself when we do zeros, and then we measure it against our sample. And so this bellow is our sample bellow. So I'll thaw all of my oxygen into the sample bellow, equilibrate it for about 6 minutes, make sure that I'm not fractionating my sample, because when you're looking at any isotope, you want to be sure that you're not fractionating it. And then I will start the run. And so this is the basics of how I run the line. Yes, that's what I've got. I guess I could push back the laser and give you a better idea of how the sample looks size-wise. So if you look in here, we've got our sample holder, which is the little piece at the bottom, and then our chamber, which is this whole container. And we've got a nice glass window that makes it great for us to be able to see what's going on, and it allows the laser light to pass through and laser sample. So this whole chamber gets filled with the reactants, and yeah, just to give you a size idea, the holes are each about 4 millimeters wide in diameter. And yeah, that's pretty much the end of my explanation for how the line works. Thank you all so much for letting me participate, and I'll be happy to take questions at the end if anyone has any. Great. Okay, Natasha's gonna make it back to the office.
Thank you, Riley. That is very impressive and actually also very professional.
Yeah, I will say I have had a lot of fun doing these analyses. I didn't realize how excited I would be to be working like as an experimentalist in the lab. But I've been having a great time, and it's just a really exciting entrance into graduate school. So I'm grateful that Dan has let me work in his lab with him and you know, use some extraterrestrial samples in his terrestrial line.
Yeah, totally. And also, yeah, I think it's also good for him to have you in the lab for sure.
For sure.
Yeah. Okay, so okay, so I think the official like show and tell is over, so maybe it's a Q&A session now. Does anyone have any questions? You can put it in the chat box, or you just unmute yourself and just yeah, just shout out.
Yeah, that was it was really interesting run through of the scope of your work and then the day-to-day process of making that data. It was really interesting to see your plate that you're using to collect the freshest calcite. I didn't realize it would grow that quickly, that you would be able to grab it in the process. How fast do these stalagmites normally accrete, and does that help you make an age model for them also, collecting it in the process?
Yeah, so usually I think something that we tell people is they can grow as fast as your fingernails. That's kind of like the average, but then there are also definitely either ends of that sort of like normal distribution. But they can grow every other. So we've been leaving out the plates every other month, and we've had enough calcite to scrape off to get enough for stable isotopes. Traditional stable isotopes, unlike triple oxygen, require 50 micrograms. So if we are interested in doing triple oxygen on the plates, we would have to leave them for much longer to accrue 6 milligrams. So I think that's definitely something to think about. But then other than that, I think it's hard to kind of piece together an age model just based on the modern, seeing how fast they're growing, because you can have seasonal hiatuses and you can also have hiatuses in the stalagmites as they're growing. So this is one that we just collected as well. And over here, you can see this sort of like sanded banding, and that's a clear hiatus. So who knows how much of time we have lost. And in order to do that, it's typically uranium thorium ages that help us build. But the cool thing about these plates is we can actually look at seasonal differences. So if one system is more affected by the summer monsoon, we are putting out plates when they have these convective storm cells passing through. So then we are able to see, okay, it rained above the cave, there was a massive convective storm cell. Did that signal show up in our plates? And use that information to translate to when we're inferring speleothem data.
That's really interesting. Other questions from folks? I've got another one if so I could go for it. So when you're integrating a technique with you know, less intensive research behind it, like the triple oxygen stuff you mentioned, you know, not as much of a workhorse technique as others, you know, Delta 18O, 13C, etc. How does that influence how you design your study from the start? Did that affect the logistics of knowing how much sample you'd need, etc.?
Oh, wait, could you repeat the question again? The initial part got cut off.
Oh, yeah. Just it was when you're working with a approach without as much of a track record behind it, like the triple oxygen stuff, does that affect your study design going in? Did you have to make any adjustments and take any different stuff into consideration that you wouldn't have with like traditional Delta 18O stuff?
Yeah, so I think we will always be sample limited working with speleothems because you only get so much. So I think that's something definitely we have to think about. What we do is we cut them into slabs. So we have more surfaces to work on. So this is like the middle section of that stalagmite. So we now have like 1 to 4 surfaces. So one surface can be dedicated to triple oxygen and another surface to traditional stable isotopes. Something else that we are also interested in is fluid inclusions. We have collaborators that are interested in fluid inclusions on these samples. So for that, we have to make sure that they're in ambient air temperature, so they're not stored in really cold spaces or very warm spaces. And then we're also interested in paleo floods using the quantum diamond microscope, so looking at magnetic properties. Some of our collaborators are interested in that. And for that, they wanted to make sure that these samples are not placed in the same room where the lab is, because all these mass specs have magnets. And they come from that point of view where they are concerned about that, the magnetic field influencing the magnetic field of the speleothem. So it's just, yeah, having all those considerations before we go in and collect stalagmites or collect specimen.
Well, I wouldn't have thought of that. I just seen an article about meteor specimens and concerns about magnetism as well. Um, um, so where is your work going to take you next? What's the next steps for you in this project?
Yeah, I think so the next first immediate steps are getting ages, because we have all these interesting questions on whether, and so variability has changed through the Holocene. What does that look like in the tropics? What about, I'm also interested in periods of abrupt climate change, like Heinrich events, Heinrich stadials. How are those signals expressed in tropical paleoclimate records, specifically from the Philippines, where you have the Sunda Shelf exposing itself? But all of that kind of hinges on the ages that we get. So depending on the ages that we get, can we tease out millennial versus centennial versus subdecadal or multi-decadal scales? Will just depend on how fast or slow they're growing and what the ages are. So that's going to be the next first step to get ages.
I have a quick question about triple oxygen isotope measurement. So it sounds like the ARMS actually measuring the molecular oxygen, and it seems like it can get oxygen, I mean the 17 and 18 at the same time. Is that correct?
Yes. Okay. So it's molecular oxygen until it gets into the mass spec, and then it's ionized by the filament in the source.
Yeah.
So yeah, you can measure all 3 isotopes. So you measure the small delta 17 and small delta 18 values at the same time on the same sample, which is really great. Yeah.
Yeah, I'm just kind of curious, like, have you test like the oxygen, like the O18, I mean O18 from the triple oxygen measurement compared to the gas bench? Like, are they the identical, or they have some sort of a systematic offset? Just kind of curious. Because from the gas bench you get a O18 as well, right?
Yeah, I'm not too sure. I only know about what I've been running in this lab, but maybe Natasha has some insights into how it compares to other methods.
Yeah, I think that definitely there is intense research being done where Dan and one of his graduate students, Justin, are measuring O17 and O18 on waters. And we also have a Picaro instrument, and we are running internal standards. So the Picaro instrument also tells us O18 and O16, and they're comparing those values to see, because it's currently in the method development stage.
Yeah.
So really, box that in very well. And they're not the same. There is fractionation happening in the oxygen, but that is an external check to make sure. I think we'll feel confident in our numbers when the Picaro O18 is similar to
the
oxygen.
Yeah, because I was thinking like you can get oxygen 17 and 18 from triple oxygen isotope measurement, but maybe you still want carbon isotopes, so you're still gonna need a gas bench. I mean, talk about stalagmites. So sounds like you still need to do a sort of a same measurement for, at least at the same depth or same age. I'm just trying to think about this. I don't
Yeah.
know. I think it's, yeah, I always am fascinated about all those new techniques and the new stuff we can measure. Yeah, thank
Obviously,
you.
you have to measure DSMs to make it even more confusing. Like just add another offset measurement to try to cross compare.
I think it really helps increasing the robustness of the climate, that signal that we are then finally getting, right? Like getting all these different multiple parallel approaches to best understand what the climate is doing.
Yeah. Cool. Thank you. So I do not see any questions from chat box. What do you think, Dan? Maybe we should wrap it up.
Yeah, I think this has been a really great run through, and I'll add to our compendium of, because we're going to post this on YouTube as well. So I think it'll be a great, reference for people to see the work you're taking. And it's been interesting for me. I'm a clam guy, but it's interesting seeing how these stalagmites, though they're inanimate, a lot of overlap in the concerns that I have versus what you have. So it's been cool to see, and it's exactly why this speaker series is so enlightening. So yeah, I think it's we can wrap it up.
Cool. Okay, so thank you, Natasha and Riley again, and thanks everyone for coming. So like Dan just mentioned, this will be uploaded to YouTube. So hopefully you can contact Natasha or Riley or us if you have further questions. Thank you.
All right, thanks
Thank
everybody.
you.
Bye bye.